I'm Dr. T, and welcome to my whiteboard. So today I'd like to talk about solutions not just in the sense of what's in them and how those individuals interact, but in the sense of how much is in them. Solutions are mixtures, and mixtures are not in fixed ratios, so they can differ not just by what they are, but how much of what they are. So I can imagine I've got two solutions, and let's pretend the blue dots are my solvent. Keeping in mind that while water is an important solvent, it is not the only solvent out there by a long shot. So let's say blue is my solvent, red is my solute. You'll notice that these two beakers are different. This one has a lot more solute than that one. Now, if I look at these two beakers, I've actually got a slightly different story. The amounts, the total sum of both solute and solvent, are much lower in the one closer to me. But if you look at, say, the ratio of solvent to solute, you've got a slightly different story. I've got 4 times the volume in this one as opposed to that one, and I also have 4 times the solute. It's as if it's the same mixture, but just less of it, and that is the case. What we're getting to is this idea of using a ratio to describe our mixtures. A ratio that is the part, or the solute, over the whole, which is usually the solution, although a couple of times we will treat that as if it's the solvent. More on that later. Okay, this is an idea we call concentration. Of course, any idea needs some good units, and I have several over here. The ones you're probably most familiar with are percents. So you can have the mass of the solution, or the mass of the solute divided by the mass of the solution. And in that case, you have a percent weight per weight or mass per mass. Now you're thinking, okay, but what if it's the liquid? Well, you can do exactly the same thing with milliliters. But here's the catch. Milliliters aren't grams. For water, they're pretty close, but for other things, they're not. If we're thinking of a milliliter of mercury, that's a lot of grams there. That's like 13 grams. So these two numbers may well be different. So we do distinguish these guys. So we will have a percent sign, and either m/m or w/w if you're saying mass or weight. You'll see either one used, although not intermixed typically. For the mass unit over the mass unit, it doesn't have to be grams. It can really be any mass unit. It could be pounds or kilograms or elephant weights, whatever you want. Likewise, volumes can be any unit so long as they're both the same. So I can have milliliters and milliliters. I can have gallons and gallons, elephant volumes and elephant volumes. Okay, this is getting kind of weird, but you know, it works. And what I'll get is a percentage. Now this number, of course, will be a decimal. Because decimals are inconvenient to work with, we multiply it by 100. Just shift the decimal point over 2 spots. Now, more than likely, it's going to be a number that's, bigger than 1. And we'll put a percent sign on the end to tell you, hey, we did move that. And we'll put v/v. Now, there is an interesting quirk. Quite often, your solute is a solid and your solvent is a liquid. And solids are easier to weigh and liquids are easier to measure by volume. And, well, if you think back to the old days when the metric system was young, the gram was defined as the mass of 1 milliliter of water. So you actually have a pair. And in most systems, you get these pairs, grams and milliliters, kilograms and liters, if they're both 1,000 times larger, but even in the English system, a pint and a pound. A pint is a pound of water. Well, in this case, we're going to create this kind of faux canceling of units. We're going to say grams cancel with milliliters. I know they don't, but let's pretend they do. And so this, you'll have a weight percent. So you'll have grams divided by milliliters times 100% to get rid of that pesky decimal point. And we'll say m/v or w/v. Typically, depending on what your solution is, will be which one of those you use. But you ask yourself, wait, what if I've got something that doesn't have much solute? What we would say is very dilute. Well, in that case, maybe 100's not big enough. Maybe I need something bigger. In fact, I could use any number I would like. The popular ones are 1,000, or sorry, not 1,000. 1,000 is particularly unpopular because it's too close to 100 to be useful. But a million works well, 10 to the 6th, and we call that a part per million. A percent's really a part per 100, but no one calls it that. So in this case, I have one part, remember, my part, per the whole, and it's per million parts of the other thing. Alternatively, I could go billion, if it's even smaller, or higher, parts per trillion, etc. Now, that's all said and good, but chemists, we love our moles. We really do. So, we have a couple of units, and our favorite unit as chemists is molarity. I even colored it in blue for that special reason. So, molarity, which gets the symbol capital M, technically it's capital M, written the size of a lowercase m. I know, that's weird, and like no one does it, but that's the official rule book. Molarity is going to be the moles of solution, or moles of solute, my bad, over liters of solution. Now in this case, you can't swap out the units in the old time. Those are your units. Is this number too small for you? You can use metric prefixes. I could say millimolar if I want to move it by a factor of 1,000, or nanomolar if I want to move it by a factor of 1,000,000,000. Now, I have molarity. One oddball that we're not going to deal with much right now, but we'll come back, is called molality. Molality is particularly popular when densities will be changing, specifically when temperatures change. In that case, I still have moles of solute, but instead of liters of solution, which, hey, as things get hot, things expand, so this number will change, and well, it goes the other way when it gets cold, I have kilograms of solvent. As I mentioned, there's a couple of oddballs here. So I get molality, which is abbreviated lowercase m. Yeah, just like meter, you got to use some context clues to figure out which one's which. So yeah, we've got some units, and we're going to stick pretty hard on this one because we love our moles. Now, you've got some units. You can describe your solution, but you can also describe change in solutions. So if I go over here, I can imagine a scenario. I take a concentrated solution, and I take some of this concentrated solution, something that has a concentration more than what I want. I take some of that out, and I put it in a new container. I then add more solvent, whatever solvent I want, and I fill it up to a new volume. Typically, when we add a solvent or mixed chemicals, we fill to a volume instead of pre-measuring of the solvent. Turns out some chemicals like to slip and pack even tighter together. Alcohol and water are notorious for doing this. So we measure the final volume, not the intermediate volume, because they don't always add up. So I could transfer over some volume and add more solvent. This is going to have a higher ratio of solvent, or more appropriately said, a lower ratio of solute, a lower concentration. Now, I can do some math to calculate this. All I need is an equation. The equation I like to use is C1V1 equals C2V2, although quite often you will see it as M1V1 equals M2V2. The C stands for concentration, and the V stands for volume. The alternative form, M1V1, assumes you're working in molarity, which, if you're a chemist, you probably are. Once again, we love our moles. So, we can say the initial concentration multiplied by however much we moved over, which, if you think about it, if we're dealing in molarity, the concentration and volume will get you to moles of the solute. You're looking at how much solute you've just moved. That's going to equal, well, the same amount of solute, the concentration and volume of your final product. In theory, this volume could actually go down. You can remove solvent. It's difficult, and usually we're adding solute, but the math works in either direction. So I can take the concentration initial, however much I move over, the volume, and use that to calculate the final concentration, or frankly, any piece of information I'm missing using this equation. So let's use the dilution equation in an actual question, or two. So looking at this question, I've got a dilution taking place, and in my narrative, I see how much 12 molar hydrochloric acid is needed to make 250 milliliters of 2 molar hydrochloric acid. So I want to go down in concentration, so I'm going to go up in volume. So I'm going to take C1V1 equals C2V2. Once again, you can write it with m's. It's perfectly fine. I'm going to do some algebra. I'm going to get V1 by itself. I'm going to plug in my numbers, and bada boom, bada bang, I get myself a value. Now, on this one, there's one thing I'd like to point out quickly. For starters, you'll notice how your concentration units are going to cancel out. And you only have the one volume unit. It's going to transition over. Your volume unit is not directly interacting with your concentration units. So you can use any unit you want. Molarity is moles per liter, but I'm using milliliters here because the molarity has completely canceled itself out. I can use percents, I can use whatever I would like, as long as I can consistent, as long as I use the same unit over and over again in that particular equation. So in this case, I'm using milliliters and molarity. That's fine. Do I want to use, say, parts per million and gallons? Works too. Whatever the answer I would like, I can use those units. Now, of course, let's go for a different question. So I'm going to take what concentration of NaOH is yielded from diluting 25 milliliters of 5 molar NaOH to 250 milliliters. And this is kind of the way we word this. So we're going to take this amount of stuff, so that's my C1 and V1, and I'm going to dilute it too. So that means I'm going to take this, I'm going to add solvent until the final volume reaches 250 milliliters. And once again, in this case, it probably wouldn't be a big deal. Presumably, this is both aqueous setups, but it is possible for different solvents to mix in ways that the volumes don't add up. So we usually just kind of fill to a mark. We don't add our solutions. We don't say, okay, I'm going to add whatever 250 minus 25 is to it. 225, yeah. Okay, moving on. Of course, what concentration? That's screaming C2. Okay, same setup. Dilution equation, algebra, plug in the numbers. Once again, the volumes are canceling now, so I can use milliliters, I can use acre feet, whatever I want, because they cancel. They go away. So molarity is left over. Once again, I'm using molarity in milliliters. It's really popular for chemists to do, but you can use any unit you'd like. This is basically just algebra. I'd like to introduce you to a technique known as titration. In this technique, you're going to be doing a chemical reaction and using that to help you figure out the concentration of an unknown solution. Now, to do this, you will need the concentration of a known solution. So the way this takes place is we use an instrument known as a burette, and we take a solution and we add it to another solution. Now, in both cases, we're going to accurately measure the volumes. The solution in the Erlenmeyer flask was measured accurately to start with, and the burette is going to have accurate graduations on it so that you can measure the amount of solution that has been delivered from the burette. The next piece of information you need to know is the concentration of one of the two solutions. So in this case, I'm going to be titrating hydrochloric acid, which will be in the Erlenmeyer flask, with sodium hydroxide, which is in the burette. From the burette, I have dispensed 35.35 milliliters of my sodium hydroxide, and I know that that's 0.1 molar, very accurately. Typically with titrations, you are dealing with pretty high precision here, 4 sig figs at least. So I've titrated that in there, and it's gone to the end point. I have used some form of chemical, typically phenolphthalein, but I could also use others that are going to either change color or, in an interesting case, change smell. You can use onions, go figure. Alternatively, I can use pH probes or other ways of knowing that my reaction has completed. I need to know that I've added just enough chemical to completely react all of the chemical in the Erlenmeyer flask, so that I have effectively both chemicals being the limiting reagents. This status is known as the end point. So when I titrate to the end point, I have added just enough, but no extra, chemical from my burette into my flask to complete the reaction. Technically, I've gone just a little bit over, but we're hopefully talking only a few fractions of a mole. So hopefully it's not enough that's going to affect our significant figures. We're hopefully well beyond what kind of significant figures we already have. So tiny, tiny amounts of them. Okay, so I've done that, and I know I started out with 25 milliliters of hydrochloric acid. So this actually is going to look a lot like a dilution equation, even though it's nothing to do with the dilution. So I'm going to set up a dimensional analysis, and these tend to get just a little long. So I'm going to set this up. I'm going to have my initial amount that I added of my known. Of course, I'm going to be working with molarity, and I want to work with moles because I have a chemical equation. I'm going to have a balanced chemical equation here. So I need to get those milliliters into liters. So boom. I'm going to use my concentration. That is going to convert my volumes into moles. And then just like a normal reaction, I'm going to go moles to moles. Yay. And at this point, I want to get into conversion. I have moles, but I want to convert into molarity. So I need to add a volume unit. So I'm going to add a volume unit. The moles are already on top. In this case, they're not going to cancel with anything. They're just going to keep on going right to the end. So I made my volume unit, but that volume unit is in milliliters. Now I could have in advance done the conversion, but in this case I didn't. So I'm going to add one last step to get my volume unit in liters, because once again, molarity is moles per liter, so they need to be moles per liter. At this point, milliliters of sodium hydroxide has canceled with the milliliters, so now it's liters. The sodium hydroxide has been converted from liters into molarity, so the liters are now gone, and it's now moles of sodium hydroxide using the molarity. And then I've converted from sodium hydroxide to sulfuric acid, and now I have moles, sulfuric acid, I've added back in my volume unit, made sure I had the right one, and I'm back to molarity, but this time of sulfuric acid. You can think of this in some respects very much like you did with other reactions, where instead of using a formula weight, you're using the molarity of your solution. Thank you, and have a wonderful day.